Good evening, CFP, and welcome to the fourth lecture in the Perspective series, an introduction to the arts and social sciences. Before we begin, we want to thank Dean Samir Shah, the program chairs Kat, Vishal, and the CFP and CEP logistics team, Dhruvika, Judith, Nupur, and the IT and communications departments for their help in putting together these lectures. A huge thank you to Dr. Leslee Lazar for accepting our invitation today. And a little bit about him. Dr. Lazar teaches at the IIT Institute Gandhinagar. He got his Ph.D. in neuroscience from the National Brain Research Center and did his postdoctoral research fellowship from the Harvard Medical School. Today's talk focuses on charting a history of ideas around the brain and its function, and shall cover how advancements in neuroscience and modern medicine have shaped our perception of the brain and its function throughout history. So please put your hands together for Dr. Leslee Lazar.
Thank you. I don't see anything. So, thank you for the warm welcome. Can you all hear me? Yes? Yes? No? Okay. End of a long day, I suppose? Yes? Maybe you guys can finish your selfie and all that right now before we talk. We've been trying to get this to work for an hour. It worked for about 20 minutes, and at the right time it has failed. So perhaps it's something to keep in mind about what we're going to talk about. Cyborgs, technology, humanism in the future. So I generally don't give talks like this, which means, science. Can you hear continuously? There's glitches, right? So this is also not working. What I thought I will talk about today is sort of a larger perspective of, how is neuroscience related to certain ideas in society. The things that we take for granted, the kind of language we use, the kind of implicit understanding that we have about how people behave, what the brains do. So that's not something that neuroscientists do on a daily basis. We really focus on one problem, we do experiments, then we try to understand how the system works. But I will not want to bore you with it, so I'm going to step back and talk a little bit about the history of ideas, the history of what the brain was in the earliest recorded history. Okay, so we need to make this full screen. No. Can you ask him to come here? You know what to do? Okay. I just have to. Okay. And all those videos are lined up. Well, let's. Okay, so that's what we're going to talk about. So we will trace the idea from. Okay, now it's working. Okay. All right. So this is where I work. This is IIT Gandhinagar. If you guys haven't visited us, please drop in. We're by the river Sabarmati, and we have a amphitheater which was built during the COVID time, so we haven't really used it yet. And then we have a really nice sports arena which hosted the national games. So it's pretty good. I saw the fastest Indian run, and बोर्ड खराब हो गया अभी तो काम कर रहा था maybe we can keep talking. I'm always curious about what people think about certain things. Um, so how many of you are really worried that artificial intelligence and machine learning algorithms they will take over the world? How many of you are worried about it? Some kind of dystopian future? Raise your hands. How many of you are worried? Okay. The rest are not worried. That's good. So, can anybody tell me what exactly is going to happen? Like, what is your worry? I understand with nuclear technology and all that, right? But with AI, I really don't understand what are you worried about. Can somebody articulate your fears? Surely it's not the technology of the overhead projector. That's definitely not going to take over the world because no, that's not going to happen. Yeah, please, sir. Jobs, a lot of machines also took over jobs that were done manually. For good or bad, I'm not making a judgment here. But yes. But anything more specific? Because it's kind of relevant to what I'm also going to talk about. You know, um, how many of you heard of DeepMind, the Google AI platform? Okay. Yes. Hold on, hold on, hold on. Okay. Now, hopefully. Yes, hopefully we can start now. So I was showing you our very beautiful athletic and football field. This is where I work, so please do come and drop in. Um, Jump right into the question of what do we know about the brain. So I was trying to see which was the earliest idea that we had about the brain. Okay, so the earliest evidence that humans actually thought something that's inside the skull is important comes from these skulls that were excavated about 6,500 BCE in Spain and in Peru. So they had these um, holes in the skull which were quite symmetric. I mean, it looked like it was man-made. You do find a lot of these skulls with head bashed in was not a very uncommon sort of discovery in paleontology. But this was a little different. It looked like people were doing some kind of ornamentation. Okay. Now, there was another skull, there were a series of skulls around that time in the world which had these patterns that were very man-made. All right. So, in India also you would find these skulls in Lothal and Kashmir. In India, actually, you do find cow skulls with this kind of man-made holes in them. So this was the earliest evidence that humans thought that, hey, whatever is inside the skull is is doing something, and they're trying to reach it. We really don't know what they were trying to do. And this was all before the death. So it was not some kind of ornamentation of the skulls or something like that. And this idea actually stuck around for a long time. If you see this painting by Bosch, there's this guy getting his skull drilled. So it was commonly known at that time that if you had some kind of mental illness, if you open up a little bit of the skull and let the spirits go away, you will feel better. We now know that it's a wrong idea, but think of this idea that has lasted, 8,000, 9,000 years. It's still, Bosch was in 1800s, I'm not sure when, but this idea stuck around for a long time that if you drill holes in the skull and remove the spirits, perhaps something will feel better. Now, the counterculture also, the counterculture movement actually took that upon. Even in the 70s. People were actually drilling holes in their skulls to feel better, reach a higher state of consciousness. But that's not true. I'm not recommending that you do it or try it with your friends. So stay away from the electric drills, and it is a bad idea. And the history of the brain actually has a lot of bad ideas. We will trace them little by little. So that's the first idea. The second idea is I'm going to figure out which is the earliest mention of the word brain. What is the written evidence for the brain? So this is, who's this? Lara Croft. But she didn't sell anything to Edwin Smith, but Edwin Smith was this British Egyptologist, meaning he will talk to tomb raiders and buy these scrolls which are stolen from the tombs. And so he bought a papyrus and he started deciphering what was written on it. Okay? And it turns out that it was a very ancient script. It was dated to 30 BC, written in symbols, the hieroglyphics. It was not a language. So this had first description of brain. And this is the symbol for the brain. Okay? It does look like a computer mouse, but it probably is not, because this was 2,000 years ago. Now, this also was mentioned 48 times, and it was a description of head injury. So it was almost like a medical text. I'm not sure if they could completely decipher the entire document. I'm only going to stick to the description of the brain. So this is, I think, a photograph of the real hieroglyphics, not the same one, but something similar to it. And this is what was written. Instructions concerning a gaping wound in the head, penetrating to the bone, smashing his skull, and rendering open the brain of his skull. If thou examinest a man having a gaping wound in the head, penetrating to the bone, smashing his skull, and rendering open the brain of the skull, thou shalt palpate his wound. Should you find at the smash which is his skull, these corrugations which form in molten copper, something therein throbbing and fluttering underneath your finger, like the weak place of an infant's crown before it becomes whole. He discharges blood from the nostrils and there's stiffness in the neck. This is this doesn't seem like something that was written 2000 years ago. It's quite modern. They're giving you a nice analogy between how the brain would feel, if you actually put your finger on it, if somebody has a brain injury. And also they are describing the correct symptoms. There's going to be bleeding through the nose and the neck is stiff. And the diagnosis is this cannot be treated, which in many cases even now is the same, right? So you might think that the Egyptians actually thought the brain was very important, given the fact that they had a very good description of it. In fact, the Egyptians had this habit of preparing their kings and queens to the afterlife by mummifying and placing their bodies with everything that is needed for the afterlife. But if there's one thing that they actually required in the afterlife, they were not actually allowed to take it with them. They did not think that the brain was anything useful. So what is happening here is this guy is putting a metal spatula and scooping out the brain. So when somebody is dead, they're going to remove the brain, then mummify the body, and then send them to the afterlife. This is also a bad idea. If you assume that you need the brain for the afterlife, or if you assume that there is an afterlife and all that, it's a very bad idea. And this bad idea, permeates for a long time. In fact, Aristotle was one of the first experimental biologists, as they would call it. Look at what he says about the brain or the heart. The heart, which is naturally hot, he determined must be counterbalanced in the order to attain the mean, the true and the rational position. Thus, the brain, which is naturally cold, tempers the heat, and when the brain cools, the hot vapors reaching it from the heart, phlegm is produced. It's a real mess. They've not properly understood what the brain is. They assume that it's a cooling device, and then phlegm. We spit out phlegm. Why is phlegm important, right? So these bad ideas permeated for a long time. And I'm just going to summarize it in one slide, but this went on for thousands of years. For example, the psyche, the soul, mind, and vital principle, is made up of the lightest, most spherical, and the fastest moving atoms. We know that's not true. Slightly cruder atoms are concentrated in the heart, making it the center of emotion. We know that that's not also true. And the title, The Heartless Cyborg, I think is slightly making sense to you, because people are placing a lot of importance to the heart, which is nothing but a pumping device. All of the processing, all of emotions, all of perceptions happening in the brain. People did not know it at that time. Here, blood was the medium of thought, and the degree of intelligence depended on the composition of blood. Another bad idea, totally false. Plato, reason or intellect lies in the brain, but divinest part of us, the immortal soul, mortal soul, lies in the heart. That's also wrong, right? So one of Plato's problem with trying to explain human behavior and whether you should have education for everybody, whether you can learn, whether you can change your human nature, was clouded by his idea that the natural laws subordinate to the authority of divine principle. So he believed that certain things are inborn and they are divine principle and they cannot change. Okay? So we talked about Aristotle right now. So there were, I'm not saying that it's always, you know, the bad idea. There were different varieties of bad ideas. Okay, they were not only saying that the heart was the center of everything and the brain was not. Some did make a little compromise. So Avicenna, the great physician, placed the sensation, cognition, and movement in the brain, which is what we do in modern neuroscience. Okay, but which in turn he believed was controlled by the heart, right? So that's another problem. Even though he got half the question right, he did not get the rest of the question right. So, if we were to build a cyborg for the whatever functions that you want, whatever functions you want to enhance from what we have right now, certain ones you want to enhance, certain you want to minimize, you really do not need a heart. That's what I meant by that title of a heartless cyborg. I did not mean it to be, a mean and a cruel device. Okay, I didn't mean that the cyborg is going to have only negative emotions or any such thing. It's just that we really do not care about the heart. I know I'm, putting down the heart, but I'm only tracing the ideas of the brain, and it's nice to have a villain. So, and also how these ideas sort of permeate our culture. We still think of heartache as something that happens in the heart, but I think if you question the person once or twice, they themselves will say that no, it's not really happening in the heart. It's just where you feel it. It's sort of visceral, feeling in that part of the body. So in fact, there was an interesting study where they compared the brain activation of physical pain. You hit somebody's thumb with a hammer, and then you ask the person to talk about their, ex-partner, whom they've recently broken up from. And while they were doing these two tasks, their brains were scanned to figure out which part of the brain was activated. So it turns out that they were both in the same part of the brain. So what it means is that there is no difference between this physical and emotional pain. It's a construct that our brain creates to give us this feeling. And the trigger can be anything. It can be a loud sound, it can be a punch in the gut, it can be your finger being smashed by a hammer, or it could be a breakup. All right? So, so here in the 1001 Nights, the Arabian Nights, 439th night, when the Caliph savant asked the brilliant girl Tawud, "Where is the seat of understanding?" She answers, "Allah casteth in the heart, where its illustrious beams ascend to the brain, and there it becomes fixed." So you see the ideas from the Arabic physician and scientists seeping into their culture and coming into popular literature. Okay, and you see that quite often across history. So I just want to take a small pause and get everybody on board about what the brain does. Of course, it's a very difficult question to answer, but if I were to paint with a very large brush, I'll divide it into, it has a sensor, which, it doesn't have, it is a sensor that can detect light, sound, touch, chemicals from your tongue, nose, and everything. So whatever you're perceiving in the external world, it's going to somehow know what's happening. Okay? Then there are some calculations it does. And those calculations actually manifest as your perception, your learning, memory, decision making, and everything. And in real time, perhaps it's perception, but it's not like a tabula rasa. It's not like there is nothing inherent in the brain. What I mean by inherent is not something that you're born with, but you do have, learning, education, whatever you've learned, the social structure and things like that. Those are also computations that the brain makes. These are also the assumptions that the brain makes. So all our attitudes and beliefs and culture, the embodiment, all of that also is sort of the base on which these functions occur. Now, last part is the output. The only output we can make is movement. except say sweating, right? Apart from that, every other output that you make, the way I speak, it is a motor movement. The way I move my hands and legs, they are movements. So this is, in a nutshell, in the broadest of brushes possible, what the brain does. Okay? So, and the goal of the brain is survival, of course, or else we would lose certain parts in evolution, we would gain certain parts in evolution, and it's a very dynamic process. Now, just want to, this is very high school stuff, but I thought we'll get everybody on board. We have a brain here that is connected through the spinal cord, and these are peripheral nerves, so that you have control over the entire body. There are two kinds of nerves broadly. One is the input one, which gives you all the perception stuff, and all the processing is going to happen in the brain, and then you send it out through what we call as motor neurons. And they're generally separate kinds of nerves. There are some mixed nerves as well. So broadly, you can divide the brain into lobes, and these lobes generally have one singular or a bunch of functions that could fall under one category. For example, if you see the back of your brain, so this is the forehead and this is the back of your brain. The back of the brain is where your sight is processed. All right. So among all the senses, we have visual people. You're all architects. You're always drawing, taking photographs, and we always judge buildings based on how they look. So this whole part is the visual part of the brain, which means if somebody gets injured or there's a stroke in that area, the person would become blind, even if they had perfectly working set of eyes. Now, so the front part, let's go to the front part. The front part is sort of a master controller. Okay, your personalities, your attitudes, whether you want to do certain things, your high-level decision making, all those parts are in the frontal lobe. And if somebody has a lesion or injury to it, you will find personality changes. Okay, you will see them do things that are very uninhibited, things that you and I would not do in a social setting. Those people would do. So a neurologist, just by taking the case history and what the behavior is, can easily figure out, they can actually quite, to a large extent, exactly describe or predict where the lesion is, where the injury is, by just asking questions, asking them to do little tasks and things like that. So the front part of the brain is what we call an executive function. It will control how much memory you will have. It will control your whether you can do quick calculations, how you behave in social settings, anger, all those kind of things. Now the middle part, here is where the touch is processed, and that's an area that I work on. So my lab, IIT Gandhinagar, we work on trying to understand how the brain processes touch and how we use our tactile abilities to perceive different things. And then the movement also is somewhere around here. So you might have seen these videos in the popular press where the surgeon is doing a surgery in the brain and the person is awake, and then when they stimulate that particular part of the brain, the hand moves, right? So that's because this part is specifically controlling all the movements in the brain. So most paralysis happens because this part is damaged. So the person cannot move their hands. And there's a separate area for hearing. The memory is all inside. It's a three-dimensional structure. So if I were to cut the brain, it would look like this. So this is also a cut brain. So the memory is somewhere localized here. And the cerebellum is a place, it's called the little brain. It is responsible for coordination and balance and things like this. So this is, and the stem on which, so the brain is actually like a cauliflower, you can think of it. There's a stalk, and then there's one layer, and then there are, like the floor, there's another layer piled on top of it. So the more central you are, you're going to find functions that are very vital for survival. Okay? Say, for example, maintaining your heartbeat, temperature. breathing rate and things like that. So any injury that's going to happen here in this stem area, in this area, is going to be fatal. But any injury that's going to happen here is only going to have select deficiencies. We can live without language, right? You can, or even with the laws of one hand, one leg, not a problem at all. Or even vision, that's not a problem, you can live. But when it comes to here, it's very difficult. So this is a MRI scan. You must have seen these. These are pretty sophisticated machines which cost a lot of money, and they can take a snapshot of the brain. How many of you gotten an MRI done if you've broken something? Nobody? Okay. So you know what I'm talking about. It's that whole donut-shaped machine. So you get a real sense of what the physical structure is, what damage is, and things like that. You also have a souped-up version of it where you can figure out which part of the brain is active when a particular task is being done. That's not available commercially. It's done experimentally across the country. There are only a handful of these machines. It's called fMRI, functional MRI. Okay, so you would get readouts like this. So all these red parts are where there's more blood flow. And depending on how you set up the experiment, if I make somebody listen to music and then check the fMRI, I can then see which part of the brain is taking more oxygenated blood, and then I know, hey, this part of the brain is responsible for listening to this kind of music. So that's the kind of logic with which we work. So I wanted to show you these pictures because I want to now step back. Oh, there's one more slide I forgot before we step back. So I just wanted to talk about a common blueprint of the brains for pretty much the entire animal system. So we have fish here, amphibians, reptiles, birds, small mammals, and these are large mammals like horses. And we have the human brain also. Now, you can subdivide these brain areas. Don't worry about the names, but just look at the color. Okay? So if you were to compare a shark's brain and a human brain, it looks totally different. Right? One looks like it's a mangled, I don't know, whatever it looks like. And the human brain looks like this. So you might not think that there is an underlying commonality between these animals, but no, there is. It's just that whichever part is more useful for that animal in that environmental milieu, that part has sort of become bigger or expanded. All right. So you see the red part here. This also has a red part, followed by a pink part, blue part, the light green, and the yellow. The same thing happens with the human brain also, but this is such a small part here for the shark, and look how big it is for us. It's always larger for the mammals, and this is the cortex. This is where the seat of all our higher level functions are. The reason we have the sophisticated perception, we are able to build objects, we're able to build concepts, this whole, you being architects building stuff, no animal has that. And that is because it's attributed to this enormous expansion of what we call as a cortex. And look how striped this is. Like even for a horse, it's quite striped. And this is quite bald. The reason why it's striped is that there's a lot more surface area. It's like you take a bed sheet and you crunch it up, you'll find these, you'll get these wrinkles. It's essentially wrinkles on the brain. So that's one thing that we have expanded, right? But we've also lost some things. If you look at this part, this bulby thing in the front is what is used for smell, all right? So the reptiles have a good sense of smell, the frogs have a good sense of smell, even fish have, and even small mammals seem to have a good sense of smell, right? But we don't actually have anything protruding like that in the beginning. In fact, it's sort of completely regressed and it's lost inside. That's because we really don't use our sense of smell like rats do or even dogs do. So depending on what function fits us, we have the brain that is performing to that capability. All right. So now I want to go back in time, and after you've seen those images, um, let's go back to the Renaissance time, where so the pre-Renaissance was we didn't have very detailed neuroanatomy. We did not know how the nerves looked. We did not know how the muscles looked. You all must have heard of Leonardo da Vinci, right? He made a lot of drawings in neuroanatomy. Also, I'm going to show you one. And right at that time was this big revolution happening. And one of the revolution was that people's ideas about dead bodies changed, that you could actually dissect the dead bodies. It was still difficult. People had to go and steal from the mortuary, or you'd have to wait for a public execution of a criminal. It was okay to dissect them. So in many a times, these dissections used to be like one big TED talk. You know, whatever is a TED talk now used to be these public dissections. In fact, in the town of Tübingen, I remember that because I was in Tübingen a few years ago, once they had two criminals being hung for whatever reason. So the prince actually gave a holiday. The king said, it's a holiday today, and after these people are hung, there's going to be a public dissection of the body, and you will learn about science through that. So with that in mind, with that advancement in thinking about the body, you could get a lot of neuroanatomical information. So the one person who is perhaps the best neuroanatomist in history is Vesalius. And he was the greatest of the Renaissance anatomists. And before that was somebody called Galen. We don't have to worry about Galen. And if you look at his diagram, so this was a book published in around 1530s or something. It's very, very similar to what we find in our brain scans that you just saw. Okay? So they did not have any problems in describing these material structures, these physical structures of the brain. But still, there was a little bit of problem about attributing where the functions are and what exactly is the driving force for everything. Now, you do realize it's a time where the spirits and all those things still held a large sway in all of science and medicine. If you go to a doctor will not tell you that, oh, your spirit's bad. I mean, a good doctor shouldn't, but these days you never know. So this is also Leonardo's diagram, and look at, I want you to focus on one particular part. So there is this part that he's drawn it as quite big. This is actually a space inside the brain which is filled with water. Not really water, let's call it water. It's like it's a very valuable thing. So it's enclosed into the hard shell of the cranium, and it also needs some shock absorption if you hit your head against the wall. So you have these empty spaces filled with this fluid so that it floats nicely inside the cranium so that it doesn't sit. And then if you move your head, it sort of nicely floats. But this is the real size of it. This is sort of a textbook picture. The portions are fairly correct. But if you look at these pictures, there's a large amount of emphasis given to that space. Instead of looking at the tissue around it, they're more concentrating on this empty space because it fits in with their idea of spirits. Okay? So they believed that the brain actually had some spirit, and so if you want to release the bad spirit, you probably drill a hole and take it out or something like that. So they did have problems attributing the right functions, but the anatomy was on point. Now, I want to talk about another philosopher, Descartes. How many of you heard of Descartes? His famous quote. What is his famous quote? Yeah, I think, therefore I am. Yeah, so that's his quote. But there's one idea of his. Have you heard of duality, Cartesian duality? Right? So we're going to talk about it. So now from the spirits, you need to somehow come to the material world, right? So he was the first person who said that, look, it's all material stuff. Right? Everything is based out of atoms. molecules and tissues and something like that. So the animals and other forms of life are actually machines. This is the first idea of your cyborg coming into picture. You know, there is no psyche, there's no soul, there's no life force. It's all materials. And the animal spirits were actually a physical entity, that is the chemical liquid. He was quite right. This is the neurotransmitter he's talking about, serotonin, dopamine that you've heard about. Of course, he didn't know that. So he didn't say that all our thinking is based on something magical. He says it's nothing but a special class of volatile chemical substance. In fact, at that time, the biggest technological feat were these fountains in the Palace of Versailles. So he actually compared the human mind to the fountain there, the mechanical hydraulic fountain. Now, this kind of analogy, now we all say that, hey, human mind is a computer, right? You must have heard that. We have a hardware, we have software, cloud software, and all those things. But there's a long history of metaphors. When Pavlov, heard of Pavlov? Pavlov's dog? So he actually used to write in his papers about the telephone cables, because telephone was the magical invention at that time. So he would say, hey, this is like plugging the telephone wire into the main board, and this is like to the sideboard, and whatever technology that was. And then when they discovered the nerves, they realized that the nerves of electrical impulses passing, electricity was the biggest thing. In fact, electricity and the discovery of electricity inside the brain happened very parallelly, and they were talking about, oh, these are these telephone wires or these electrical wires that are going from the tip of your finger or your feet to the brain. So, all these analogies and metaphors sort of always were there, and it's not going to end with computers. Whatever is the next big thing in the nether 50 years, you're going to compare the computer with. There was one thing that he did that sort of resonates even now. So he talked about a duality. Okay, the physical substances are material, extended in space, and include particles which can be observed and measured. Now, mental substances, in contrast, cannot be examined, for they do not have any material basis or fixed location in space. Now, this is a big problem that we are still facing the repercussions, because if you say you're depressed, we don't actually deal with it the same way when you say, I'm having a digestion problem. Okay? We somehow don't think that it's all a material manifestation in the brain. It's biochemical, it's electrical, whatever. But we think that it's not. There is something in our thinking that is a leftover of this dualism. Okay? I'm not reducing all depression or all of your moods and your everyday qualia to an uncontrolled biochemical reaction. No, I'm not saying that. Okay? But even these biochemical reactions can be affected by what you do. So it is the substrate for thought, but he did not want to say that all of our imaginations, thoughts also have these physical bases. And I believe there's a political reason for it. This is the time the church is getting a lot of human phenomena, social phenomena, by reducing it to atoms and things like that. And the church was sort of feeling Hello? Yeah. So he made this separation saying, look, let me play with my dead bodies, let me do my dissection, let me figure all these things out. If the church wants to say the mind belongs to them, it comes from God, so be it. I'm going to say that there's no material basis for it. So, of course, he didn't say it in the same way that I said it. I am reading history and interpreting it for you. But he, of course, built an entire starts from him. And yeah, you can so actually placed in one part of the brain, and that's the pineal gland. And so this is his idea of the brain, and I showed you pictures of the brain. Doesn't look. I don't know the specific reason why he put it. That's not the seat of consciousness. Consciousness is a distributed sort of function all over the brain, and it emerges from all these electrical activities. Right, but can you hear me now? Yes? Okay, that's good. So even the reflex, the simple reflex. So he did figure it out. He said that the information is going to go to the brain and then you're going to move your leg. So you can say that he got a lot of things right, and it's the start of thinking about the brain in material terms. So then it went on to look at, hey, is the brain going to have the same function from the top to the back? No, it has separate functions. That was a completely different story that people had to figure out just by looking at patients with certain deficits and then trying to predict where the hole in the brain is, and then wait for them to die and then take out the brain and figure it out. So that was a completely different stream of thinking. So let's now go into the idea of what is the brain made of, right? It's a tissue, so it's going to have some kind of unit that it's built of, right? What is that unit? So the cell theory came around 1770, 1760, I think, when Hooke could see a slice of cork under the microscope, and he figured out that there are these cells. So all tissues, is made out of cells. But is it the same cell? How does it look? What are its function? We didn't know until these two guys started tinkering about in their kitchen. Okay, this is Golgi. He's an Italian guy, and this is Cajal. He's Spanish. So he actually invented a technique where you cut the brain in very thin slices, very, very thin slices, and then you put some dye into it. And because, a tissue doesn't have any differentiation if you magnify and look at it. It's just going to be white, right? So you need some coloring substance. So he made this stain, which we still don't completely understand how it stains, but it stains the neurons beautifully, only stains the neurons. See, all the other tissue there will not be seen. So now you can actually look at a neuron. And this man, in his kitchen, backyard, started doing a lot of studies on how the tissue looks like. Now, this is what a neuron will look like. This is a cartoon version. This is a real neuron, actually. This neuron is not black in color. We put some black color dye, and somehow we are able to take a photograph of one particular neuron. Can you guess how many neurons we have in our brain, approximate? Any number? Millions, billions, billions. Millions or billions? Billions, okay. How many? 1, 10? Huh? Just a number. So people used to overestimate the number. People thought we had 400 billion, 500 billion. But in the last 10, 15 years, there's been quite a lot of advancement in the way things were counted, the brain cells were counted, and we know that we are around 85 billion neurons we have. Okay? So this is how a neuron will look. So why I said that is it's a technological feat to just take a photo of one neuron among 85 billion neurons. And then you can have fluorescent dyes. So you put the, you soak the tissue and then you look at it in a specific wavelength so the cell sort of glows up. Now all of these cells have this head and this kind of axon as we call it, and these endings. So all these 85 billion entities are all connected to each other. This part will be connected to the head of the previous one. So when you look under the microscope, you really did not know whether these were specific individual entities, 85 billion of them, or it's just like a mass of stuff. And that was the controversy between these two guys. This man thought it was a congealed mess of everything. He didn't believe in the neuron theory. This man said that, hey, wait, these are actually independent neurons and they're connected. In fact, they had such an acrimonious debate, they would fight all the time, and they both were awarded the Nobel Prize at the same time. They shared the Nobel Prize. They went on the train together to get the Nobel Prize. They didn't talk to each other. And in the Nobel Prize acceptance speech, they attacked each other. There was such a dirty business going on then. But one thing they did well was, like you guys, drawings. So these are actually illustrations of neurons that this was done by Golgi, this is done by Kahal, and you can actually Google and you can find this book in the public domain. It's absolutely gorgeous. And there are different kinds of cells, there are different kinds of structures, and if you look under the microscope now with all the latest technology, you wouldn't add too much to what they drew. They were so good with their technique, with the simple techniques, that they could actually figure out the structure of the nervous system to a great detail. These are some more pictures. If you look, recently I saw some art piece, and I was like, wait a minute, where have I seen this before? And that person had not attributed it to Kahal or Golgi, and they basically lifted some of his circuit diagrams and included in their art. You will, once you're familiarized with this, you will find this quite often in popular culture also. There are a lot of books written about it. So how am I doing on time? I lost track because it's okay. Okay. So now we have these 85 billion neurons, and I said they're all interconnected, but they somehow have to communicate with each other, right? Your neurons' language of communication is the electrical activity. So if you notice, you must have heard of this famous experiment by, was it Walter? Galvani, right? He's saying that the frog's leg is going to twitch if I give it electricity, right? So he's going to give electricity here, and then it's going to twitch. So what he says is that there's some kind of animal electric energy in the muscles. It's not true. It's not true. Even before he did this, or right about that time, there were people looking at the electric eelfish, which actually has an organ which shoots electricity to fight against its predators and run away. So there is this idea of electricity, and there is this idea of bioelectricity. Now in the neurons, obviously we're not zapping people around us, but each cell has a certain voltage potential. And if it wants to connect and speak to the other cell, it's going to send an electric spike. Just like how if I want the current to flow through the wire and the light bulb, the same thing is going to happen inside the brain also. So there's constant barrage of electrical activity that is going around here and there. So the language of the neurons, the way they connect, is biochemical aspect, where we have neurotransmitters. Serotonin, you must have heard about dopamine and things like that. But that happens in spaces between the cells. Okay? So in the cells, if I have one cell here and another cell here, there's going to be a voltage change, an electric spark that is going to travel, and then when it's jumping from one neuron to another, it's a chemical thing. So you could think of it as both electrical and biochemical. Okay? Now let's forget about the biochemical part. Now if you have this electrical part running around. What if I inject some current in some part of your brain? Say there is a part of the brain that is required for memory, okay? Will I be able to make some changes with your memory? Now, this patient is called Henry Molaison, and he had very severe epilepsy. So back in the 50s, they actually did not, in the 40s, they did not know a lot about what different parts of the brain did. They did not know that this part of the brain is very vital to make new memories. So what the doctors did is, in order for him to have a normal life, they operated on him and then cut out that part and threw it away. So this man does not have hippocampus. So what do you think his symptom is going to be? Any guess? Sir? Somebody there? No memory, yes. He is not able to form any new memory. Okay? So this man was studied by neuroscientists for almost 70, 80 years. He passed away just 5 years back. And he gave such a wealth of information about what this particular part, this hippocampus, does. So now the question is, if we know that there is this particular part that is going to be important for memory, so this man would meet the experimenter almost on a weekly basis, and every time the experimenter has to introduce, hi, my name is this, oh, can you sit down, can you do this task, and he will not have any recollection of how he walked into the room, who the president was, what he ate for breakfast, absolutely nothing. Almost like this movie Memento, where this person has anterograde amnesia, not able to encode new memories, which was ripped off by the Hindi movie. So you have these localization of functions, and then you have this electrical activity, right? So what if we can do that? So now we are trying to think about the future, right? So we're trying to think about, what if we have a cyborg, and then we are able to stimulate part of their brain. We realize it's electrical activity, and we've tamed electrical activity, right? We have power generators, we have DC batteries, and we only need a very small current to inject into the brain. So can we do that? Okay.
Electronic mind control research is not new. A scientific milestone came in the 1960s when Dr. Jose Delgado created remote charging bull. By connecting a radio antenna to electrodes inserted into the bull's brain, Delgado proved that the animal's transit impulses could be thwarted by electronically manipulating the bull's muscle reflexes.
Do you realize different? We could modify the system inside, but the beauty is that now we are not using electrodes.
In recent years, Delgado has shown that the behavior of monkeys can be altered using low-power pulsating magnetic fields. But in these experiments, there were no antenna implants.
Any function in the brain, emotions, intellect, personality, well, could be perhaps modified by this non-invasive technology.
Delgado's research has so far been limited to animals. But in the Soviet Union, a radio frequency, or RF device, has been used for over 30 years to manipulate the moods of mental patients.
Okay. Couple of things.
ठीक भी होगी आपके हार्ट भी बढ़ेगी नहीं कौन भी बुलाएगा मेरे बच्चे को छोटा
Yeah. Today technology is not my friend at all. Sure. So you have to take this with a large pinch of salt. But for this talk, it's okay because we are thinking about how society, politics, everything intersects with this kind of neurotechnology. We also have a showman now. You know the showman's name? In this day and age, there is a showman about brain technology when he knows nothing about it. Yes, he actually was a good scientist. And so one thing that he said was in the video was kind of misinterpreted. It did not interfere with the muscle reflexes of the animal. He had actually implanted the wire in the brain. So he was actually controlling the area of the brain that sort of has the stop movement sort of function. So with the radio frequency device, he was able to switch on and inject some current in that part of brain, and so it stopped. So the bull stopped. So this demonstration in bulls is very dramatic. People thought that once you have this wow factor, then you're going to listen to me more, and then so he will talk about his ideas of how you can have a society where you can get rid of all the bad things and keep only the good things just by brain stimulation. In fact, he wrote a book talking about a neuroethical society, but nobody really listened to him. It's just some kind of a fantasy. Showmen generally have a shelf life of 5-6 years, and then after that nobody will listen to them. So but the idea is there, right? So the idea that he showed, this has actually become a pretty routine thing. I have done it in the lab. You can actually stimulate certain parts of the brain to figure out what it does. And also, it's there in everyday clinics, even in Ahmedabad. Every city, you have these clinics where you can inject a little bit of current to either stop or start certain part of the brain. So this is a good application. This is not a showman application. This is routinely done. So Parkinson's disease affects a part of the brain called the basal ganglia, which controls repetitive movements. Okay, and so now I'm doing this repetitive movement. I have total control over it, but people with Parkinson's will not have control over it. So they'll have something called the resting tremor. The hand will keep vibrating. So in order to stop this, what doctors do is they would implant an electrode right into this deep part of the brain. So can you see the orientation of the brain? So this is the brain, and it's now cut in half to show you where this place is. So you would stick an electrode here, and then you string the battery device, and then you have a pulse generator, a pacemaker sort of thing in the chest, which will give you the command to stimulate this particular electrode. And if you take an CT scan of the person after it's done, this is what it will look like. Fairly routine, and let's see what it does. Should work. Okay.
The probe that is placed into the brain, I understand, comes level with the top of the nose and the ear. And it is connected to a battery in my chest, in the skin of my chest here. And this is controlled. I can control the amount of the voltage going in. I can control the length of time. The number of times per second that it goes in.
The machine.
love your child, your wife, or your husband, being absolutely locked inside their body. I would say that you have to be a zealot not to allow research to be done on animals in order to cure this love.
So you saw how powerful the stimulation was and how debilitating the disease is, right? So the moment he switched it off, he had absolutely uncontrollable tremors. You can't live with those tremors on a daily basis. You can't even sit down. And he said if he concentrated 90% of his energy, if he can concentrate, he can control a little bit of his tremors. He couldn't even have a conversation with another person. Imagine living like that from when you wake up to when you go to sleep. And magically, not, I use magically in a very non-magical way, the moment he switched on the device, didn't even take a minute. Within a few seconds, his tremor went away, right? And and at the end, he's talking about the objections to research, and when it started, there was a lot of objection to putting these implants into the brain, right? Because it is an invasive process. You might have some infection, and people still don't know which is the right place to zap the brain. But thankfully, for Parkinson patients, it's a trade-off, right? Do you want to live with a tremor like that, or you might have some kind of small side effects? I'm not saying this is a magic bullet, but if you give the choice to somebody who suffers from Parkinson's like that person, obviously going to take it, right? So anyway, moving back to stimulating the brain with electricity. Now we're all convinced that we can do that, right? You could do it to stop a bull from running towards you, or you can use it for. Now we will also watch a couple of videos on how this technology can be used for other functions. So in this video, I'll skip the video, but I'll tell you what is important. So here the technology is a little different. You're not shoving the electrode into the brain, all right? You're just using a cap, and you're using metal electrodes on the surface of the cap. So this is called non-invasive.
Safe and user-friendly, and it's non-invasive. So we use electroencephalography. This depends on the ability of the subject or user. Learn quickly, he can use from the beginning all three. So the main purpose is to develop such system which could be useful for people, elderly people, or people with limited mobility, or disabled people, handicapped people, or partially paralyzed people.
So here, instead of putting it inside the brain, you can record the brain activity from the surface, and EEG is quite cheap. We have it at, there are obviously very cheap technology, and there's also expensive technology where the fidelity increases. We also have this set up in IIT Gandhinagar, and this is a new way of thinking about it. What if you can record the brain waves that are happening when the person is thinking about moving left or moving right, okay? You have to decode that algorithm and then use that signal for your advantage. And for this person, it's the wheelchair, okay?
They can use such wheelchair in the future without any assistance, and they can move, they can improve their mobility and independence. Stop. 10 more right. Yes, more right. Stop.
Do they continue to function?
So this is the last video. So this is again going back to the invasive idea. Okay. So you can do both. You can record activity from, where are the slides? So you can both record the activity from the surface of the skull, like here, using the EEG signals, and then you do some kind of processing, right? You want something that can quote unquote read minds, but it's not mysterious like that. Just like how we can control our breathing, control a lot of our body states, we can also control certain waves. All you need is a feedback. So all of you can do it. If I have an EEG set up here and I program it to say a circle increasing and decreasing based on your brain waves, and tell you to reduce the circle, you will be able to do it. There's no magic in that. If that person in the wheelchair, right, he's able to have 3 or 4 different signals of, say, move right, move left, move front, stop, just by using his brain waves, we can also do it. Okay. But sometimes sometimes the signal gets complicated. If it just move right, left, it's okay. But what if we have multiple degrees of freedom? You want to have very complicated control of the system. Then you want this computational power to be complex, right? You want that to be advanced. So you can get the signals out, do some processing, and then it can give a signal to your prosthetic leg so that you can walk, or it can also give you a signal to the prosthetic hand so you can feed yourself. So this part is now going through a transformation because of AI algorithms and things like that. So let's now look at one particular technology called the brain gate technology, which was developed by the Brown University in the US. And they have done a few clinical trials where they've implanted these electrodes into the brain, and then they're able to decode. And these are patients who cannot move their hands or legs. So their brain is healthy, it's active, but because of trauma or some other reason, their spinal cord is severed, or they have ALS or some other disease where their muscles don't work. So they need some other actuator to work like their hands and legs. And let's see this last video.
In this paper, 2 people with tetraplegia, and it's 2 people who are unable to move their arms or their legs in any functionally useful way, were able to control a prosthetic or a robotic arm simply by thinking about their own as they were their own limb. The robotic moved much the way their own arm would move. One of the long-standing questions, not only in after that original injury. It is possible for people to use their thoughts to control devices, either a computer or a robotic arm. The way that happens
is that we implant a tiny sensor, just about the size of a baby aspirin, just into the surface of the brain. That sensor pick up the electrical impulses from a bunch of neurons.
When all of us saw it for the first time, gave us all pause. She reached out with the robotic arm. She thought about the use of her own hand. She picked up that thermos of coffee, brought it close to her, tilted it towards herself, and sipped some coffee from a straw. And that was the first time in nearly 15 years that she had picked up anything and been able to drink from it solely of her own volition.
There was a moment of true joy, true happiness. I mean, it was beyond the fact that it was an accomplishment, I think an important advance in the entire field of brain-computer interfaces, that it was really a moment where we helped somebody do something that they had wished to do for many years. This is the culmination of more than a decade of work, beginning with science at Brown University, that laid the foundation for all of the translational work that led from monkeys playing video games using their thoughts to humans being able to control a cursor in 2006 to ultimately to today's accomplishments.
This kind of research can only happen when institutions come together and bring together teams of scientists, engineers, and physicians to work closely together.
Okay. So, okay. So you got an idea of what is the cyborg part now, right? So in the future, maybe you can have this amalgamation of neurotechnology and what it is, and our human powers. Maybe we can attenuate some things. Maybe we can modify certain things. This is very rudimentary technology, but it helps us to think about it right now, so that we will be prepared when the technology is available to us. And now we have social media, we have fake news, we have no idea what to, we had no idea that this is going to happen. Little did we know in the 90s that, we're going to be debating what is truth. We thought that was known. So perhaps this is a class for you young people to think about, the post-human reality perhaps. I don't know if that will happen. I don't know how it will happen. There are a lot of technologies that failed. There are a lot of overblown promises and things like that. But the power of AI/ML algorithms, I'll give you a few examples of them. Back in the day when Kasparov beat the Deep Blue, it was trained on chess moves. Okay? So now they have this new kind of reinforcement algorithms, which earlier started with the data of all the chess games in the world, and then the algorithm would learn. Okay? And then now, so in 2022, this AlphaGo is an algorithm by the DeepMind. It beat the European Go champion. So Go is a Chinese game, like Chinese checkers. I'm not sure exactly what it is, but it's a very, very difficult game. It's apparently more difficult than chess. It needs a lot of strategizing and intellectual power. But this computer beat that person. So nowadays you cannot beat these algorithms in Go and chess and shogi and any other strategy games. And this development happened over 6-7 years. Initially they had to be fed with data for them to detect the patterns and then learn how to behave in any particular scenario. Now the algorithms are so complex that they don't even need the data. Oops. Okay. So there's another game called StarCraft. I'm not a gamer, so I'm just reading out these names. That also apparently uses a lot of strategy. And for the first time, a computer, an algorithm was able to play at a grandmaster level. And these are happening pretty fast. There are a lot of computational problems, challenges that were there for 50, 60 years that have been really crunched really fast by this AI/ML technology. And I would urge you to Google DeepMind, and they have a really nice website to explain what their algorithms do and how they're using it in healthcare, how they're using it in weather prediction, how they're using it in neurotechnology and things like that. So one big thing is going to be these algorithms getting more and more powerful. The second thing is cheap neurotechnology. So now you can buy this EEG setup online. This costs only a few thousand rupees. And you also have NeuroSky, which is, I think, exactly 9,000 rupees or something like that. And you have a starter kit where you can actually program some games with your own mind power. So this technology also is growing, and it's getting more and more accessible. So combining these two things, I think the cyborgs of the future, that is us, is going to be a really interesting time. So I want to end with that thought of, in the post-human future, what will be the role of neurotechnology? What can it enhance? Can it minimize? Can it modify? Will it change the humanness? Do we have to face a new post-human entity and create new set of ethics rules and a new kind of society? So that's the whole question about this post-humanism, right? Are these rules that we've been living with for the last thousands of years enough? Do we have to completely rethink these ideas? I'm not an expert in such a thing, but perhaps with neurotechnology, perhaps with some ideas about how your thinking can be changed, how the brain can be modified for good or bad, how does that lend itself to this question? So with that, I would like to end, and thank you very much for your patience, and I'd be happy to take any questions if there's any time. Thank you. Yeah, 10, 15 minutes is fine, yeah. Oh, yeah. I'm not, yeah. We'll just shut it. Oh, your grades will be, yeah, please.
Yeah, so we just spoke about how with neurotechnology we can punch in algorithms into an AI, right? So can an AI actually be sentient in the future? There are many controversies regarding that, but I really want to know if it can be.
I really am not the right person to answer that question. I don't know what it means for an algorithm to be sentient. I don't think, I think all those ideas came about from an extrapolation of what can be done. Right now we know that they're learning at a fantastic pace. If you look at the last 5 years, it's a little scary how much these algorithms can learn, and sort of, if you had a checklist of things that are only human, the kind of decisions that we make, the kind of games we play, we thought that the machines will never be able to beat us. But in the last 5 years with this DeepMind algorithm, a lot of things are being checked. But being sentient, will they emote? Will they be able to smell something? I don't know the answer to it, and perhaps that question is perhaps not well posed at this time and space.
Okay,
I know I didn't answer your question.
So the video we saw about the experimentation on the bull, the one where they inserted a radio transmitter to send electric shock. How sure are we that it was actually affecting the neuro elements of the bull's brain, or was it just conditioning, like a shock collar, so it's sending a shock to an aggressive response, and it's just...
So there are many ways one can check that, right? If you were to implant the same electrode about 5 centimeters away in another part of the brain and give the same amount of current, will that also stop that bull? If it stopped, then I would say maybe it's some kind of shock, but this is very specific to certain areas, Okay? So the area that was responsible for this kind of defensive movement and freezing was stimulated. And there are other experiments where there's an interesting experiment where they stimulated an area called ventral tegmental area. This is an area where it's processing the pleasure signal. So they implanted this electrode in the VTA, and you sort of gave a lever for the rat to press so that it will stimulate that area. It was almost like the rat is taking a cocaine hit every time it's pressing the lever. And the rat actually pressed the lever so much that it starved to death. So, so these are very specific functions, and you're stimulating exactly very small areas of the brain with very, very controlled electrical pulses. So it's not a general effect.
And related to this, like, does electrotherapy have like any medical background to this? Like, is it related to it?
What is electrotherapy?
Like shock therapy. Like it's an old age.
Yeah. So it does. So I hear from my psychiatrist friends that for the recalcitrant depression patients who cannot be treated with any kind of therapy, medicine, and they're completely not functional, it's sort of the last resort therapy. But it's not as inhuman as it was portrayed in the movies, One Flew Over the Cuckoo's Nest and all those things. So it's all done under anesthesia now and with muscle relaxant. So, but I have seen a lot of papers also that show that there's a lot of improvement in the depressive state. Of course, there are some side effects, but it does work.
Okay, this is in regard to schizophrenia, where people have delusions. So what exactly happens in the brain when a person is in delusion? Like
Okay, so I really don't know. I'm not an expert in schizophrenia. I don't study schizophrenia, so I know my specialty is in touch perception. Maybe we should stick to that. We can discuss that off camera. I don't want to end up saying something that is untrue. So I don't know much about schizophrenia.
I wanted to ask, what was the case with Stephen Hawking back during the day? How did he used to talk and communicate?
I think, if I'm not wrong, I think he had a progressive motor degenerative disease, which means that all his muscles sort of did not take the signals from the brain, right? So that's why he couldn't use any of his hands and legs, and even his, the voice box sort of stopped functioning. So what you do is you sort of tap into any signal that he can control, and then you give it to an actuator. I don't know the exact details of what he underwent, but in many patients, if you have people who are completely locked in, right, meaning they absolutely cannot move anything except an eyelid, right, then you would put a little electrode in the eyelid and then communicate through that. In fact, anything that the person can change. In fact, there was a paper there was a patient in Germany who could only change the pH of their saliva in their tongue. That was the only thing through which they could communicate. So these people implanted an electrode in their tongue which would record their pH, and then you would have yes, no question, that kind of stuff. I know it's a scary scenario, but at least there's a window to communicate with them. You can check what Stephen Hawking had done. Any other questions? Go ahead.
Yeah. Even it's true that this whole robotics and AI is making our lives easier, but at the same time, isn't it dumbing down the humanity? Like, for suppose, instead of dumbing down the innate abilities, like the inbuilt abilities that the human could possibly access through the subconscious, for suppose the using of telepathy instead of phone or. So please correct me if I'm wrong.
No. You can continue with your question.
No, it's just I want to know your thoughts about this.
Yeah, so we don't have telepathy. Do we agree on that? We can't communicate without speaking or writing. Yes? And the innate abilities that we have, I don't know how much innate abilities we have. I am of the belief that we have very, very basic innate abilities, like breathing, maybe moving towards the food source, being in a warm, moving towards warmth, avoiding cold. Those are the innate abilities that we are born with. Rest of it we learn from the environment. Of course, there are neural systems that sort of push us to learn in one direction. Okay, so that is one thing. So I want to object to the fact that we don't have telepathy. I want to make that clear, and I also want to make it clear that innate abilities are not what you probably think it is. It's very basic stuff. Now to the third part of whether you're dumbing down, I don't think so. I think it's, any piece of technology, any science, any advancement is very value neutral, right? It can be used for good, it can be used for bad. We scientists tend to think we are saving the world, but we also invented the machine gun, the bomb, the nuclear weapon, poison, global warming, all that kind of stuff, right? So there are good and bad things, and I'm not sure how to address this question of if we use certain neurotechnology, it's going to dumb us down. Some might, and some might enhance. So that's what I was, urging you guys to think about. What are the technologies that can make us better, perform better in a task? What are some things that are going to make us perhaps less optimal? Like, you don't have to think about only AI. You can also think about all the other computing stuff that we have. A lot of us cannot do mathematics anymore. A lot of us don't do arithmetics. In fact, I have very bad spatial navigation skills because I just use Google. And I actually remember only one phone number that is mine. So you could say that, I have become dumbed down because of these technologies. But one needs to sort of think about it a little bit more carefully and not, have a broad picture. I know it's a new thing, so we are processing it. So we need to sort of sit with it and engage with it and figure out if it's a good thing or a bad thing, or it doesn't matter.
So apart from the tangible material aspects that the human could actually have the ability to do, the other extra sensory perception things like, as such I've mentioned before, don't even exist like at all.
You mentioned telepathy and I said no, but if you can give me an example of what you call an extra sensory perception, we can...
like child prodigy or clairvoyance or...
child prodigy is you set a benchmark and then you say if you score above the benchmark, that's a prodigy. So I've seen child prodigies playing piano and all that. That happens, it's real. But clairvoyance, I don't think anybody can see the future. We can have this conversation, we can have a long conversation on that.
Yeah, thank you.
Okay, thank you.
So we're collecting so much data about the brain, and if you can actually store it and work on it, then is it possible to actually recreate a person's consciousness?
The same idea was pitched by a scientist in Switzerland, and he said that I'm going to make an artificial brain. And then he said, okay, I'm just going to make a small sliver of the brain and make an artificial substitute for that. Even that he failed. So I know we are collecting what seems like a lot of data and processing a lot of information, but I don't think that's possible.
Thank you.
Thank you.
I have one question, sorry.
Sure.
Yeah.
Yeah.
So in that video where the lady was able to pick the coffee can, was she also able to feel whether the can is cold or hot or anything? So it doesn't work the other way around, right?
No,
Okay.
no,
Yeah.
it doesn't. Good question. So I told you in the beginning there were two different nerves, right? One giving input, one giving output. Both are not functioning for her. They're trying to substitute only the movement part. In fact, it's very difficult to give anything to her because she doesn't have any sensation. But say, for example, somebody is an amputee. They do have sensation in the shoulder. So there are a lot of these technologies which will give you some kind of vibration. So it's called sensory substitution. You substitute one sense to another and say that, look, if you're going to grab a cup, if it is cold, you need to have a sensor for it, and then it will translate it to something else. it's a little bit more difficult to do, but it is possible in some cases. But in that, you're right. She did not get any feedback. It was just that she was able to visually sort of error correct the cup, the trajectory of the cup, and then drink from it. Yeah. So you're right there that because she was able to drink, she would have definitely felt good about it, and that's the reward, and that's why she will sort of fine tune that. So if she's going to keep doing that for 100 times because she's getting that reward. But if it spills over, then it's a punishment. She's not going to do the thing. She will only focus on what is rewarding. But that rewarding is got to do with the feeling of the task being completed and perhaps the sip of the coffee, not the sensation that comes from the finger, because those nerves are not working. Okay.
Hi, here.
Yeah.
Yeah, so like you talked about the idea of healing in sense where people are using the AI to heal themselves in some sense. So as an architect, I am also interested in understanding how neurology sort of helps in space making. So do you see a potential there of this sort of an intersection of neurology with architecture? Because I've been discussing with a lot of people, and I've been told it's like a very far-fetched goal in some sense, but.
So I am interested in architecture and neuroscience naturally. So there are a lot of intersections I see. There is in fact a field of neuroarchitecture, and they have conferences every year. So what they do is they sort of take ideas from neuroscience, or you take ideas from architecture. Like Palasma talks about, Juhani Palasma, you guys must have read about him. So he talks about the idea of tactility, which you have the feeling of tactility without touching it, visually. So we call that cross-modal perception. So there are certain confluences between these two ideas, and in fact, I'm sort of delving into some of those ideas. I can't give you a concrete example of this is an example that happens, because of the confluence of architecture and neuroscience, but the dialogue has already started, and scholars from both disciplines are talking, and I can point you to some books if you'd like.
Unfortunately, that was our last question. Thank you, everyone. Thank you, Leslie, for giving us so much to think about. Thank you, everyone, for being such a wonderful audience, asking such great questions. Until next time, have a lovely evening. See you guys. Of course.